Okay, so let's start then now getting into like really some like let's really get into the topic. Like the last lecture was only introduction, so let's start. So we said that it makes some sense to review first single particle quantum mechanics in this alternative function integral formulation. So our goal is really to go to many-body physics and also many-body the function integral formulation of many-body physics. But it's first good to get like used to these concepts in a singular context, which is a single particle physics. And this then brings us to the topic of this lecture, which is construction of the path integral quantum mechanics. Construction of the path integral. And I will always now abbreviate path integral just by PI. So what we don't want to do, we want to consider some generic single particle Hamiltonian which I give here. So typical class of problems you're interested in is of the following form. So we have some kinetic energy term here for non-relativistic particles, quadratic dispersion, and then we have some potential which we leave here unspecified, and just for later convenience let us write this as a part which depends on the momentum operator, so it's a kinetic part, and then the potential part which depends here on the operator. Okay, so we just define the operators. So I use P for the momentum operator, and I introduce K. So I mean, many times you also want to use X, but I use here K just because later I will use the variable X for a phase space coordinate. Okay, so this is just some notation. So this will be our coordinate operator. And as said, so this is a typical problem we want to study in quantum mechanics, where we have some potential V of Q, and here I consider is a one-dimensional problem, but the generalization to higher dimensions is just straightforward. So just for notational convenience, I will here discuss the one-dimensional problem, and the goal of this lecture is the following. So we want to derive representation for the transition amplitude or the propagator, which I already tried to motivate at the end of the last lecture. Transition amplitude of the propagator, which is defined as a matrix element of the time evolution operator. So we have the time evolution operator for some time t. We have some initial coordinate qi, and we have some final coordinate qf, and we want to know, or we want to derive some alternative here in terms of path integrals representation of this object. Okay, so this we just give this object also some call it star, because I will refer to it afterwards. So this is the great goal of this lecture, and let me just maybe motivate a little bit more why we are interested in this object. So I already said, like last lecture, well, the time evolution operator stores all the information about the dynamic evolution of the system. So if we know these matrix elements, we actually know how the quantum mechanical system that we consider evolves. However, let me just give you some brief further motivation. So this is actually an object which also will be easily to generalize into the many-body context. So this is like the typical object propagator that we will be also interested in quantum field theory. So what we normally do is in quantum mechanics, like in the first course, is, well, we write down the Schrödinger equation for a given problem. We try to find the wave function by solving the Schrödinger equation with some boundary conditions, and then once we have the wave function, we can calculate expectation values with this wave function. Okay. Now, when this is fine, like this is the canonical way how it is introduced in quantum mechanics, that's fine if you consider a particle in the box or whatever. If you consider more complicated problems, especially if you then go to many-body problems, I mean, it's hopeless to try to write down the Schrödinger equation and then try to find the wave function. I mean, it doesn't even make really sense. I mean, what we have, if you have a complicated, disordered, interacting problem, I mean, you don't really want to have a wave. I mean, it would be great if you could calculate a wave function, but typically we can't. So what we are interested in more complicated problems is actually then to calculate observables. Okay, so and one example would be like, it's a simple example that you have some, say, small piece of metal or whatever, and we want to calculate the conductance of the system. Okay, so we want to calculate, like, if you apply some voltage, what is the current through the system. Now this can be, in many cases, it is fine to think of a single particle problem because interactions do not play really a big role, but then you can have, let's say, some small mesoscopic device with some chaotic boundary sketching, or you can disorder the system, and you want to know, like, let's say, what is the amplitude, or no, what is the probability that a particle propagates from some initial coordinate from one side of the probe to the other side of the probe, okay? Now this probability is just given by the square, the absolute square of this propagator. Now the probability that, like, what is the probability that the particle propagates from one end of this, let's say, disordered probe to the other end of the disordered probe, of course is related to the conductance of the system. The better, I mean, the higher the probability will go through, some given time, the higher the conductance. Okay, so it's directly related. So you can just in a very hand-waving way see that this propagator actually is directly connected to many observables. So we don't have to go like through the hassle of finding a wave function, whatever, but we can immediately try to calculate like these transition amplitudes or this propagator. Okay. Now this is for the single particle problem in quantum mechanics. Now, if we then think about a more complicated problem where you have interactions, like in the quantum field theory way, well, this object nicely generalizes in the following way. Well, we can ask then for what is the amplitude or the probability that if we insert some particle at some coordinate qi at some initial time into the system, okay, and this can now be highly complicated, insert it somewhere, this particle will interact with other particles and whatever, and then we just ask, well, what is the amplitude or actually the probability that we can find this particle, or we can find particle that we insert there at some final time at a different coordinate, okay? And you can see that this is just, can be just thinking of generalizing this expression. Yeah? You start from some, let's say, ground state of some material, you create a particle at some time ti, at some coordinate, and you're interested in, if you want to calculate observables, many observables are just related to the probability that once you insert the particle here, you will find another one here, okay, at some later time. So this is, in a way, a very convenient object that you want to consider if you want to calculate observables in more complicated problems, like in let's say, real problems where trying to find the wave function is just it seems hopeless, and it doesn't really make so much sense. I mean, you cannot measure the wave function. So this is just a brief additional motivation why to study this object. Now, now that I tried to motivate, like define the goal, we motivated this, so let's see what is actually the problem of just writing down this transition amplitude. So, what is the problem, or generally what is the problem in calculating such a transition amplitude? So this now here refers to this equation. Well, the problem here in the single particle operator that we considered is that it consists of a sum of two operators, okay? The kinetic and the potential operators, and these two operators actually do not commute. So this makes all the problem of going there and directly writing some analytical expression for this amplitude here. So this is in a way the problem that we try then to. So that's the first observation, and it should become also more clear what I really mean by this in the next minutes, but we just make the following statement, that is, the non-commutativity of these two operators introduces a problem. And what the path integral now tries to do is to overcome this problem in some quite clever way. So the idea is, instead of studying first the time evolution for some long time, just study first the time evolution for a very brief instant of time. And for a brief instant of time, you can in a way overcome this problem of having two operators which do not commute, to write down then an explicit expression, quite simple, for the time evolution of a short instant of time. And then you have to somehow sum over all these short instances. So this will lead us then, like that's the main idea of the construction of the path integral, to overcome this problem by some clever trick. But before I come to this, let me just, to set some notation and like to introduce the object that we are going to use, let me just recall some basic stuff about quantum mechanics. Okay, just not recall some basic stuff, but just give some notation. Let me just introduce some notation. So first of all, well, the problem, as I said, is we have here an operator made of two operators which do not commute. So we just write down for completeness notation relations for what we know. Now, what we will use a lot is eigenstates or eigenbases of these operators. So let me just, for notational reasons, introduce the Q basis as the basis which is diagonalizes the position operator, and the momentum basis. This is like the two bases that we will use a lot in the construction, the P basis. And then let me recall that the basis is complete in the sense that you can represent the identity in Hilbert space as a sum over projection operators. Okay, so this is a projection of the Q state. If you sum over all the possible Q states, so you somehow sum up all your projection operators to generate your one in Hilbert space. So this here defines the unit operator in Hilbert space. And in the same way, you can represent the unit operator in Hilbert space by the sum over the projection on the momentum space. Okay? Then what we will need is to know the matrix element of change in basis. So basis change from momentum to coordinate representation will be given by the overlap of a Q state and a P state, which is given by the plane wave. some normalization factor. We said so it's readily, all this is readily generalized via dimensions. And then just, I mean, for completeness, say that typically what we do in the beginning quantum mechanics courses, we study, start out from some representation in a given basis. So we introduce, for example, the wave function in coordinate representation, or the wave function in momentum representation, which is just given by these matrix elements. And for example, the Schrödinger equation okay, I guess I don't have to write down the Schrödinger equation in coordinate representation, but you all know. So that's what we typically do, okay? So what we will heavily use is the resolution of unity, that you can express the identity operator in terms of integrals over momentum or coordinate states. Okay, so this will be heavily used. Now, let me just illustrate this problem here by, or return to specify what is the problem here by, let's first consider then the simpler problem where, let's say, we only have the kinetic energy. Okay, so it's very easy to derive then the transition amplitude here. So if all the problem is related to having two operators not commuting, then well, if we set b to 0, we shouldn't have any problem, and it should be easy to calculate the transition amplitude. And let's just very briefly recall how we do this. So let me return to this question here, and let's consider e.g. free particle. Where the potential is 0, meaning that the Hamiltonian is just given by the kinetic energy field. Now then, if we want to calculate this object here, or just one notation remark. So here I kept it, or no, I already specified. So what I mean would be notational more consistent is to write here the time difference between the initial time and the final time. Okay, but I mean let's just set the initial time to 0 and the final time is then t. And what I have used here, of course, is that I'm considering a Hamiltonian which is time independent. Okay? So if you have a time independent Hamiltonian, it's more complicated, but let's restrict first to time independent problems. Then this propagator only depends on the difference in times, final and initial, so let's call it t. Okay? Now, if you want to calculate this, well then, I mean, what is somehow the straightforward thing to do? This here is, oh, maybe just write down once explicitly, inserting the Hamiltonian, e squared Tm h bar t. So here we have an operator, and well, what can we do is we just insert here a unit representation of the Hilbert space unit operator in terms of a projection operator on the momentum states. Now, why do we want to do this? Because in this case, this operator here operates on an eigenstate, so we can substitute the operator just by the eigenvalue, and all this here is a very simple number. That is, we can then pull out this number here out of this matrix element, because I mean it's just a number, we can use the provisional scalar product, and the matrix element, which here generally is quite complicated because there's some operator operating on this qi state and can make anything, and then we have to look at the overlap. Here it's very simple. We put in this resolution of unity. This operates on the p state. We put out the eigenvalue, and then we have the overlap of q final with the p. And this just gives us a plane wave expression for the overlap of the final momentum with p. So what we arrive at, if we do so, is the integral over p I can turn out because of linearity of the scalar product. Then what we said is we substitute here the operator by the eigenvalue, h bar t. And then, okay, let me just be more. So then we have two overlaps which are just plane waves, okay? So this will give us some plane wave, e to the ip, then we have k final minus k initial, and some normalization factor 1 over 2p h bar, okay? Now what did we arrive at is then a sigma Gaussian integral, okay? And this we can just calculate. So this would be like one homework problem. It's a good thing. I mean, just doing one Gaussian integrals, and if I have time, I will just review at the very end of the lecture some property of Gaussian integrals, just to do this, because I mean our goal is to derive this propagator here. But of course, once you have derived it, you should make first checks. So the first check that we want to do is, once we have a path integral representation of this object here, we want to see that we can reproduce the result, which is much more easily got like for the free particle without going through all the path integral elements. So this will serve as an important reference. So it's good to have this done like two ways. Once just a simple straightforward way, and once afterwards, I'm not sure if you're going to make it as a homework or if we'll go through it in the lecture. Once to derive the propagator, I mean to derive this result starting from the path integral formulation that we are going to derive. Now, but this already, I mean, was a very small exercise, but this already tells us like now what should be the strategy. So the strategy, if you want to calculate such such matrix elements, is always well go to an eigenbasis. Use a resolution of unity. But now we see what the problem is. I mean, here we have the sum of two operators which do not commute, so we cannot go to some easy basis that diagonalizes this operator. Okay? So that's the entire problem, and we somehow want to find a trick to overcome this problem and then use, I mean, kind of this version of a calculation to simplify expressions. Okay? So this then brings me to the basic idea, which is, so I write down 4 like points, which is the basic idea for the construction of a path integral. So I just write down some words, and then afterwards we will work through the individual steps. So I should write it somewhere down where I can leave it. So probably there. And then let me also state that this general recipe is also the one which will generalize to the quantum field context. Okay? So that's why it's good to go through the path integral for single part problem first, because like the general idea in the recipe how to construct a path integral is just the same in both cases, and it's good to write this down. So yeah, somehow I guess we will recall these properties here. Now this here, and yeah, so try to put it all here on one blackboard. So the basic idea, the construction of the path integral. So the first step is, so I already said, instead of looking at this transition element for long times, let us look at the transition element for very short times and try to find some approximate time evolution or matrix element for short times. That's like the main approximation that we will do is using that we are first considering matrix element for short time steps. Okay, so find, first step, find, and here it's important to say that it's not an exact, but it's an approximate, and we have to then look in which limit it should become exact or good for our purposes evolution for a very short instant of time and this short instant of time I will call delta t, and it's just the complete time t divided by some large number n. And actually this was an idea that already goes back to Dirac, who studied this kind of matrix elements very early, 33. Then once we have found, or once we have like defined the matrix element for the very short time evolution, what we want to do is using, in a way, exactly this what we're doing here. So what are we doing here? We are changing bases, okay? We're inserting here the resolution of 1 in terms of eigenstate of this operator. Why do we do it? Because then we can absorb the entire dynamical phase. So the dynamical phase accumulated within a time t can be just nicely absorbed. Like here it's an operator in some phase vector, which is just a number which you can put up. Okay, so this is the second step that we want to do here, is to find some good choice of bases to absorb the dynamical phase which is accumulated during the evolution of the short instant delta t. And again, the crucial part here is that it's the dynamical phase accumulated due to the propagation of this approximate time evolution operator. Okay? So we use delta t, small time, to make an approximation for the time evolution operator and then absorb the dynamical phase of this approximated operator in some phase. And how we do this is using, and now I just write some down words which doesn't make a lot of sense because they're not precise at all, but just let me say it's some appropriate choice of basis in the sense like this here, the p basis is an appropriate basis because the diagonal is choice of basis. Okay, so actually I wanted to write down the 4 points here, then to work through them. I don't manage to write them down here, so I continue on the very left and then try to follow the steps on these boards here, but let's see. We'll have some more space. So then the third point is, well, once we have done this step here, so we can describe the time evolution for some short time step just by some phase vector. Well, then it's quite easy to go back to the initial problem and study the matrix element for long times, because we just have to sum all these small phases at delta t, so we have to sum over n such contributions to arrive at the total dynamical phase accumulated through the time t. So for time evolution, for time t that we are actually interested in, we just have then to sum the numbers, which are the phases, sum all the phases, recalling well that the total time t is just the sum of all these small time steps, where we sum over these n small time steps. And then the fourth part is like the part, so this is first step, write down an approximate time evolution. Okay, you can write down an operator, an approximation with some correction. We can go into some clever basis to substitute operators by eigenvalues. We can sum the phases for like the small instance to arrive at the entire expression. So this is all mathematically completely fine. So we will arrive at some expression for time evolution in time t with some correction or whatever, but then comes like maybe the one step where physics starts. So in a way you can do this all mathematically perfectly fine. But at some point there comes a step where physics starts to go different ways than mathematics, and this is when we apply the limit n to infinity, which is, I mean, the idea why we want to do limit n to infinity. Well, we do here some approximation, which is justified for small instance delta t. So taking n to infinity, we hope that this approximation becomes exact. Okay? So that's the motivation. But then, if we really want to do this limit n to infinity, like, I don't know, but I guess it's still like this, a mathematician would just like enter in crisis and say, well, what you're doing doesn't make any sense anymore. But for us, in a way, I mean, we're physicists, so we are more pragmatical. So we say, look, let's do it, let's calculate, it makes sense. There might be some rare cases where there might be some result which we get which completely surprises us, and then we have to decide, well, is it some interesting physics that we didn't expect, or is it maybe some, okay, we didn't make any obvious mistake in the calculation, but is there some problems hidden in the formula? So at some point you have to go back. But so this then leads to the notion of function integrals and all path integrals and all that. But one can always also restrict to, instead of n being infinite, to a very large n and think of some regularized version. But still, I mean, we have to make some assumptions here, and I'll try to motivate like this limit here. So this is the maybe dangerous part. Okay, so that's the program that we are going to do, and now it's just, so let's implement these ideas. So let's go through the 4 steps and see what we arrive at. Okay. Or any questions, comments, doubts? Okay, so first point, as said, let's define an instant of time, delta t, which depends on some number n, which we think right now is just being a very large number. And then use that. You can write time evolution operator for time t. You can just write as time evolution for some time delta t. By n, and then we take the n for the product of this using just the Hamiltonian commute with itself, and just, I mean, to be more explicit, maybe focus unnecessary step, just write it down in the following way. So we have n factors of time evolution for some small instant delta t. Okay? And here the time evolution is to be explicit for time delta t is given by this general class of problems that we are considering, where we have a kinetic term and a potential term, so it's the sum of 2 operators, delta t. So up to here, nothing really interesting happened. We just wrote it here. And again, the problem here is that if this wouldn't exist, well, it's obvious that we can So the goal is, let's try to change this operator to some number. Okay, so this is an operator, we want to have a number, we want to have the phase factor which is accumulated during the propagation for some delta t, and operators are hard to deal with, numbers simple. So let's try to substitute this by a number. If this wasn't present, well, go into the key basis. If this wasn't present, well, let's go to the Q basis. No, both are present. What shall we do? So up to here, everything exact, nothing really interesting happened. Let me, okay, I think I don't have to write down. So I said, I mean, it's trivial to calculate the matrix element of this, and it's trivial to calculate the matrix element of this. So the idea now is exactly to use this small parameter delta t in the following way. Let's already think of delta t being very small, and already think that in the end what we are going to discuss is a limit where we send n to infinite, and meaning that we send this instant of delta t to 0. Okay? So why do we want to use this? Because there is a nice mathematical identity which is known as the Baker-Campo-Hausdorff identity. Just write it down, which tells you the following. So if you have a problem exactly of the class that we have the exponential of the sum of two operators which do not commute, you have some identity which tells you, well, this is the product of the exponential of the two operators. Now, if we would be dealing here not with operators and with numbers, this would be somehow a trivial identity, but there we use that A and B commute. Now, A and B do not in general have to commute, so this can't be the full answer, there's some correction. And the corrections you can express in terms exactly the parts which would vanish if we are, for example, dealing with numbers or with commuting operators. So there's appearing an entire like long tail of commutators. So you can express this as a series of all these commutators. Okay. So this is known as Baker-Campo-Hausdorff identity. I don't know, probably you know this from quantum mechanics. Yes? Okay, so but Baker-Campo-Hausdorff. So why is this useful? I mean, if you have here general operators A and B, it doesn't help you anything because, I mean, you have a lot of things to calculate here and you don't know what to do. But what did we do here in the first step? Well, we introduced a small parameter, delta t. So our operators A and B are both proportional to the small parameter delta t. Meaning that here we have an exponential of something which is proportional delta t, exponential of something which is proportional to delta t, but here we have the product of the two. So this is an exponential of something which is proportional to delta t squared, delta t cubed, and so on. So there's some hope that if we make delta t very small, it might be that the idea is working out, and this can be neglected in comparison to that. Now, if we do this, so what did we need? Well, we need to do exactly that. Delta t becomes smaller and smaller, then this becomes controlled, and then we separated the exponential of a sum of two operators which do not commute by the product of two exponentials of these operators. And now again, to substitute this operator by a number is very simple, because we just go here to the eigenbasis of this operator. To substitute this operator by a number is also very simple. We just go here to the eigenbasis of this operator, and we can like substitute this operator by numbers, by dynamical phase vectors, keeping in mind that what we did is approximated the exact time evolution for some short time scale by some approximated plus some small error, which we hope will vanish in the end if we define some limit which somehow makes sense. Okay? So let me just write down what I just said in words. So if we use this nice identity, we can write this time evolution now as an approximate time evolution in the product of these two here, and then just should recall that this is not the exact story, but there is some exponential of the correction of order, so this means the correction of order delta t squared. So this is 1 plus correction of order delta t squared. Okay, so it's delta t squared, all this is delta t. Okay? Now, okay, I would like to leave like the outline there, so I would now start like writing here and then erasing. Is this fine? Yeah, if I erase here. So why does this help? Well, we already said, because now looking at matrix elements of this approximated operator looks much more simple. So this then leads us to point 2. So this was point 1, finding an approximate time evolution for a short instance of time. That's 1. Now let's go to step 2, absorb the dynamical phase accumulated in the small instant by using an approximate basis. So let's go here, point 2. And let me introduce here just some small n, which will appear now at many times in the rest, and this n will always refer to some index. Okay? So what we want to do is we want to insert resolutions of unity, meaning some integrals over p or some integrals over q, but in the end we are interested in the time evolution for the entire thing, so there's a lot of products. So somehow we need some index which tells us at which instant of time did we insert this resolution of unity. Okay, so we could call it p and p tilde and p bar and whatever, but it's clever to say, well, let's just introduce some index n, which is like the time slice at which we inserted the resolution of unity. Okay, so this operator, the time evolution, is a product of n terms. So we insert in every of these n product factors some resolution of unity, and this will be like a time slice. And why we call it time slice should become obvious in the end. And the index for the time slice will be called n. Okay? Just keep this in mind. So then let's look at some matrix element of the time evolution. Right, this is a problem we started out from, but now for a very short instant of time. And now let's use the approximate time evolution. So that's the matrix element that we want to consider now. And well, if we forget about what this is, so this is some, let's think about it as some number. Okay, that's not an operator, it's some number which tells us about the correction. This is a number just put out. Okay, so we have a matrix element of a product of two operators, and well, how do we calculate it? We just calculate it exactly the same way as we did for the free particle. So we want to change here to basis where this operator is diagonal, and we want to change here to a basis where this operator is diagonal. Okay, so actually this here already diagonalizes this operator, so this is numbered. So we only have to insert here a state, the resolution of unity in terms of the eigenstates. And this now also gives the index n en. Okay, so this operator acts on an eigenfunction, putting this resolution of unity here. This operator acts on an eigenfunction. We have two dynamic phase vectors which pull out numbers. We are left with two matrix elements. The overlap between k and p at time slices n minus 1 and n, and the complex conjugate, which is the matrix element of kn and pn at the same time. Okay? So if we put this in there, we can immediately write down what we arrive at. Describe the result. So we can pull out the integral here using the linearity of the scalar product, and get now exponentials of numbers, which are the dynamic phase vectors accumulated during the short time propagation, which is the sum of the kinetic and potential contribution. And then we have these matrix elements where we just use that these are plane waves. Okay, so this 2p over h bar is the normalization factor from this matrix element, square root 2ph bar, and this matrix element, square root 2ph bar. So gives us this vector here. So brackets, I guess. And then we still have to write down the plane wave, which is now taking into account. So this is a different time slices. This is at the same time slices, but it's a complex conjugate. So we have some difference between qn and qn minus 1, and all this divided by h bar. And then we should recall, well, there's some correction of order delta t squared. Okay. Questions? Or okay, so what did we do? Well, we just followed our program, completing step 2, finding an appropriate basis, which now somehow well defined. Well, it's the eigenbasis of these two factors, and we now have a simple expression for the time evolution for some instant time n. So now we should come to step 3. Can I erase it? So we know we have a simple representation of time evolution apart from some correction for a short instant, but we're interested in the time evolution for time t. So what we should do is we should sum all the phases, and this is the third step. So let's see. Just once more, write down the time evolution for time thing. So we have this product of the factors, of n factors. So what we calculated was a matrix element in such a step, but we want to have it for an entire product. But I mean, what can we do? So we calculated the matrix element for a short step. So the short step we achieved by inserting here a resolution of unity of with Q, in the Q basis. Okay, so this is then exactly the time evolution we calculated for such a small step. Okay, so if we now insert here always like a resolution of the unit operator, we have this matrix element for a short time step that we calculated before. Okay, so again, we want to do it here and here and here and here and here. So we should again give this some time index UN. Okay. So this is again time slice index we insert here. Now just to recall what we did in the end is the following. If we insert this here and then we want to use the calculation for the matrix element, in the end what we did is for the calculation of the matrix element we inserted a unity in the representation of the unit operators in terms of the momentum. Okay? So if we want to tackle this problem immediately, what we can also say is we'll insert here the product of these two unit operators. Okay? So this here now will diagonalize this operator here using the short time approximation. Okay, so what we in a way do is we insert a resolution of unity in times of coordinate states and momentum states. Okay, so these are now integrals. And actually we already recognize what this is. So this is an integral over Q and P. So this is somehow an integral over the phase space, the classical phase space at an instant time n. Okay? So once we combine the two steps, we see that what we actually do is we introduce at every time slice a phase integral, phase space integral. Okay? Okay, so and again this n is indexing the labeling at which time step we inserted. Now, I will just write down the final thing, and you can just, I think it's maybe a little bit stupid because it's just sitting down, but it's good to do it once. Just, I mean, what I'm saying here, just, you have the expression for the short time evolution matrix element, just do once this final step. Keep track of all the indices and you should arrive at the following expression here, which I should somehow highlight, so I write it here, which is the matrix element that you arrive at for this operator that we were interested in, which now should consist of n, because we have to introduce n resolutions of unities, integrals over P and n integrals over Q, okay? So this will be a quite large integral where we integrate. Okay, I will say something here to this limits of the integration. So each, because of the matrix element overlaps to QP, so each integral always comes with a normalization to pH bar. And then if we sum all the dynamical phases, we can write this in the following way. So we pull out factor delta t, so we know that everything should be proportional to delta t in leading order. Then we have a sum which is the phases consisting of two contributions, the kinetic and potential part. Okay, so this is just from the eigenvalues of the operators V and T, and then we have another factor, another contribution, which is due to the overlaps of the plane waves. Okay, so this is one here, and plus one. Which is multiplied with the difference of the coordinates. Because we pulled out the factor delta t here, we should divide it here, okay, because this was independent of delta t, because this was just from the overlap of wave functions, so it doesn't have to do with the time evolution for short times delta t. This is the thing. And then we shouldn't forget our correction delta t squared, but now if I put out all this delta t, so this would be a correction of all delta t because I pushed out it. Okay? So this is what we arrive at. So these steps were already did. I can erase this and then just highlight this. Okay, so this is what we arrive at. Okay? Now I have to specify here still some boundary conditions, which is that let's start with Q0, that will be like the first one which we actually don't use. It's the initial, Q initial, okay, initial step. And the Q final should be given by the nth Q. Okay, so this is just saying, well, we have here a product over many like phase space coordinates, but we have a boundary condition on the zeros and the nth time slice, which means that the coordinate is fixed by the matrix element. The momentum is free, but the coordinate is fixed. Okay? So, okay, this looks maybe first a little bit scary, but it's just, as said, a very, let's say, if n is large, it's just a very high-dimensional integral. So there's some contribution here which we didn't specify and we hope that you can neglect. But in the end, this is just a high-dimensional integral, okay? So what we arrived here at this moment is we represented, well, the transition amplitude is expressed in terms of a high-dimensional in terms of the high-dimensional integral, and actually you can specify what high-dimensional means. It's 2n minus 1 dimensional integral. Because so this is, you can verify, like if you go through this construction, you have to be like a little bit careful how often you put each term in, but if you look at it carefully, you will find that you have n resolutions of unity put in momentum, so this gives you n, these n pn, and then we have to put in n minus 1 qn's because of the matrix element. You already, like this q is already acting on 9 states, so you don't have to make some trick. So you have n minus 1 free momentum q that we're integrating on, so it's 2n minus 1. I mean, in the end, it's not important, but if you once make it carefully, it's a good exercise. So what we say is that apart from this not specified correction, up to here everything is exact. I mean, it's just mathematics that we didn't do any approximation. Now, just write down what I said several times. So at every time step, Tn being defined as n times this short instant, we integrate over the pair which I now define as xn, okay, which is given by qn and pn, and this pair defines a classical phase space. So integrate over xn, parametrizing. Do you see it if I write here? Parametrizing classical phase space. So now comes, I think I can erase everything because we only have to go through step 4 there. So now comes the observation which actually gives name to the object that we are considering here. So we observe that taken together, all these phase space points where now index n, the time slice runs from 1 to n. So these points form the trajectory, or they form trajectories in a discretized version of phase space. Oh no, actually they form a discretized trajectory. So let me do this in phase space. And this can be illustrated maybe at some drawing. So for the one-dimensional problem, we have phase space spent by momentum coordinate, and now we have here some time axis that we want to study time evolution. Here's, let's say, time 0, and we have defined a problem where we start out from some initial state. Coordinate qi, but momentum is completely undefined. Okay? And we start, but we should start at some time t with here at some time t again phase space with some, let's say, initial condition that should be on this line. Okay? On this line. Now what we did in the entire construction is we introduced like all these time slides where we integrate here over phase space. So we can think of discretizing this time all these little steps delta t. So this will correspond to delta t. Now, after we have done one hop in time, what we integrate is over entire phase space. So we illustrate this maybe at some here. So here we have an integral again over the phase space, which now would be here Pn and Qn. 0, 0, capital N, capital N. And these variables here are just some very large vector which tells you at every instant, like if you look at one fixed contribution to this integral, you should fix one value of this large vector, and this one value will just give you points here and here and here and here and here in phase space. So if you fix one value, you will get some point which should be on this line, let's say this. You will get some point here, some point everywhere, okay? Okay, I think this drawing probably is really bad, but let's think of this being the phase space, and what I'm saying is like that for a fixed value here, for a fixed vector, you will define points on all these time slides, okay? So what you will get is some kind of, if you connect these points now by straight lines, you get some sort of trajectory in your phase space, a discretized trajectory in phase space, okay? So what you integrate over here, you integrate over all these vectors in this high-dimensional space. Each vector can be viewed as a discretized path. So what you integrate in some way is over what this is it's a large integral which can be thought of some large integral over discretized path in phase space of paths which start at time 0 at a given momentum, unspecified momentum, and stop at time t at a given coordinate with unspecified momentum. Okay, so that's the path integral. Now, still there is this correction delta t, and this is somehow still still something which, well, like a mathematician, I would say, well, this is like, okay, for a fixed n, we can do it, but this can become really complicated if n becomes very large. So now, we somehow want to give this some more physical meaning by applying the limit n to infinity. Okay, and this is as said, so that's the point where physics goes different ways in mathematics, and the argument that we will now use is a very typical argument that we always find these kind of path integrals, and you're thinking, maybe we can make just 5 minutes break, and I clean the board, and yeah, and we like continue in 5 minutes. Okay? So this is now the interesting part, like the last lecture.